Dear members of the European Academy of Sciences and Arts, to round off the year, the organizers of this wonderful lecture series, Violeta, Dinescu, and Dušan Šuput, have planned one lecture that could not be more fitting at the end of the year. It is about the origin of our existence in the universe. And the second one is about poetry in the development of time. The first talk considers the question, what does physical cosmology know about our universe, and what does it not know? The example of this talk, dark matter, is a very good demonstration of how science works. Science is not about religious certainties, but about hypotheses, models, and measurements that have to be constantly tested and further developed. This is directly related to my field of work in the foundations of mathematics, physics, and methodology. I would therefore love to be there tonight to ask today's speakers a lot of questions. But unfortunately, I am on a flight back from a lecture tour at the time of this lecture. Therefore, a few introductory remarks to the lectures, beginning now with cosmology. Greek cosmology and astronomy was the first exact mathematical science that already worked with hypotheses, models, and observations. It was based on a geocentric model of the spheres in which the observer stands in the stationary center on the Earth and observes uniformly rotating celestial bodies around this position. On the one hand, this was an expression of a simple and convincing mathematical central symmetry, the spheres in the center, the observer. On the other hand, only uniform circular movements could be explained mathematically at that time. When deviations from the uniformity of speed were finally observed with better observation, eccentric points were introduced outside the center of the sphere. The sphere, the central symmetry, in the center, the observer, and then eccentric points were chosen in some distance to the central point, and relatively to this eccentric point, the planetary body is moving uniformly. Relative to these eccentric points, the celestial bodies should continue to move uniformly. Only for the observer in the center do apparent deviations occur. In methodological terms, this is called an ad hoc hypothesis. Although it explains an observed phenomenon, it has no empirical evidence of its own. At the beginning of the 20th century, in 1915, Albert Einstein introduced the general theory of relativity with its gravitational law as the basis of modern physical cosmology. This theory allows for several mathematical models, not only one model. Einstein himself initially favored a static, non-expanding universe. He was a classical physicist in the tradition of Newton, and philosophically he was a pantheist and believed in an unchanging static universe. In contrast, the astronomer from Belgium and Catholic priest Lemaitre had pointed to the mathematical possibility of an expanding universe with a Big Bang in the beginning, which is also allowed by Einstein's general relativity laws. This seemed to correspond better to the religious belief of creation. Einstein didn't like that. Einstein, therefore, introduced an ad hoc mathematical constant, the so-called cosmological constant, to theoretically counteract the expansion. When Hubble's laws of expansion were finally confirmed by the measurement and observation, Einstein, of course, is a leading physicist, and he abandoned the cosmological constant and described this ad hoc hypothesis as the greatest folly of his life. But the development of science was continuing. Today, measurements and observations show a remarkable acceleration of the expansion of the universe, different from the values of calculation in the model. For this reason, a previously not directly observable quantities was postulated, which is referred to nowadays as dark energy. Mathematically, this quantity is a generalization of Einstein's cosmological constant. So nowadays, we have a rebirth of Einstein's ad hoc hypothesis. This evening's topic, dark matter, is also a postulated form of matter that is not directly visible, but interacts via gravitivity. According to Kepler's third law and Einstein's law of gravitation, the orbital velocity of stars decreases with increasing distance from the center of the galaxy around which they rotate. However, measurements of the Doppler effect show that it remains constant or even increases. This suggests that there is mass there that is not visible in the form of stars, dust, or gas, the so-called dark matter. Of course, in principle, the laws of gravity could also be changed in order to achieve suitable predictions, but the price of changing the whole theory itself with all its consequences would probably be too high. In addition, there is a range of indirect empirical evidence, which today's lecture will report on. But once again, science does not convey religious certainties. We have to learn to live with uncertainties. This is also true in other areas of science, for example, in medicine, in the climate models, and so on. But science helps us to always better understanding of reality. Now, the second lecture this evening. What has been the role of poetry in the development of time? That is the question of the second talk, especially with respect to women, as the lecturer underlines. I think that is also a main link of both talks this evening between science and arts, because both lecturers are women. In the second talk, particular attention is given to the contribution given by women in the various areas of poetry crossed by time to understand their difficulties and merits. By the way, in Germany, I'm in the advisory board of an international center for women in the history of science and philosophy, from antiquity to, for example, Marie Curie, the famous physicist and chemist, and Hannah Arendt, the philosopher and political thinker. In the early 1990s, I could already supervise the doctorate of a female mathematician and philosopher on that topics. it does not only concern the changing or not changing social living conditions of women, scientists, and poets over the centuries. The question is, are there specific female contributions to science, for example, in cosmology, and arts, for example, in poetry? We are eager to learn more about that this evening. Thank you for your attention, and I wish you all a wonderful festive season and a happy new year 2025. Thank you.
Well, I would like to welcome everybody here, especially our guests today, and of course also our Vice President Birgit Harris and Dean Class 4 Ioannis Liritsis. And just that I don't forget at the end, I would like to wish a very happy Merry Christmas to everybody and all the best in the new year. And now I think, Violeta, you can ask Birgit and Ioannis to say a few words.
Thank you very much, Dušan. I invite now Birgit Harris, the Vice President, to say hello to us.
I just say hello. I make it very short because I know that all participants want to hear Laura and Marie. And so have a nice time, have good papers, and have a nice and wonderful Christmas days also from me. Thank you so much for the invitation.
Thank you, Birgit. And Ioannis Liritsis, Dean.
Well, here I am.
Thank
you. Thank you, Violeta and Dušan, for your 3 years of dynamic pace in keeping alive this popular colloquia that I was lucky to have co-initiated with Violeta some years ago as a Dean of Class 4. On behalf of my members of Class 4, I welcome all of you, the speakers and the participants. It's a great pleasure to attend the 2 talks today, and in particular the 2 speakers, with whom I share my interests. One more reason that I could not, I could not miss it. With Laura BAUDIS, as I have noticed, a young, fast upcoming scholar, I share our nuclear physics and astrophysics research subjects, and with Maria Duaneta Miraglia, the poetry, as I'm a lover of poetry and have published myself poets. So wisely, the organizers invited the 2 speakers because the concept of invisible matter in the universe, such as dark matter and dark energy, resonates deeply with topics, themes often explored in poetry, like mystery, absence, connection, the unseen forces that shape reality. So I'm eager to learn more from these evening speakers and the following discussion, and Merry Christmas to all of you. Thank you.
Thank you, Ioannis. Dušan?
It is a special pleasure to introduce Laura BAUDIS. I just, maybe 2 weeks ago, I read a paper about neutrino fog, and I think this topic is something really, in a way, mysterious, but it's somehow it tells a lot about physics. I think that physics is a kind of mathematical philosophy, because you have to have something real to study, to have in your hands, but actually you open new worlds by that. And Laura BAUDIS is now a Swiss particle astrophysicist, and she's well known for her study of dark matter. Well, she was born in Timișoara, Romania, and even then she developed a very strong interest in mathematics, literature, philosophy, architecture, and so on. But after the Romanian Revolution in 1989, her family left and they came to Heidelberg, and there she completed her education by earning her PhD in physics in 1999 at the University of Heidelberg. Then in 2000, she left for Stanford University, And there she was engaged in the cryogenic dark matter search experiment until 2003. Now, since 2007, she's a full professor at physics department at University of Zurich, and she still has a strong interest in dark matter and neutrino physics, and has worked on dark matter detectors. I think that's what's very exciting coming out now. And she's one of the founders of Xenon Dark Matter program, and she leads the Darwin collaboration with the aim to build astroparticle physics observatory based on a huge 50-ton liquid xenon detector. It's really, can you imagine such a huge thing to detect such small things like neutrinos? And in 2017, she was awarded ERC grant for Project Xenoscope, which conducts research and development for the construction of Darwin Time Projection Chamber. In 2021, she became a member of the Academy of Sciences and Literature Minds, and in spring 2022, she was awarded a Charpak-Ritz Prize for the French and Swiss Physical Societies. So really, I'm looking forward for this lecture. I'm sure it will be very exciting, and please give us your knowledge on dark matter and neutrinos.
Well, thank you very much for, first of all, for the invitation. Yeah, I'm very excited to be here, and also thank you for this very kind introduction as well. So I hope, yeah, I hope I can tell you something about the dark matter and how we look for it. So I will share the screen, and please tell me, tell me when I should stop. Maybe 5 minutes before or so. Okay. Okay, so I hope you can see my screen. Now let me. So this is entitled as all the dark we cannot see. So this dark matter is also called invisible matter, and we will see why. But now maybe imagine that you are somewhere in the desert, or perhaps here in the Swiss Alps or somewhere else on top of a mountain, and that you are looking at a very clear, dark sky. And when you look at the sky, you would see thousands of glimmering light sources. And of course, if you are lucky and the night is especially clear, you will also see this extended nebulous band of the Milky Way. So some time ago, of course, these objects were called nebula, but now we know that they are galaxies, and especially that they are made of about 100 billion stars. And these stars then form a spiral system, which is our home galaxy. So of course, we are part of this galaxy, so we cannot really see it from the outside, right? However, if we would be able to do that, it would look very much like our neighbor, like our large neighbor, which is called the Andromeda galaxy. You can see here this beautiful spiral structure. And this galaxy, it's a bit larger than the Milky Way, but it's about 2 million light years away. So now 1 light year is about 9.5 trillion kilometers. So what you can see here is that kilometers is not a good unit of measure for these large distances. So let's step a little back and talk about distances, right? So just the distance from the Earth to the Sun, it's 150 million kilometers, right? So with a car, it takes you 115 years. With an airplane, about 7 years. But the light takes 8 minutes. So we say the Sun is 8 light minutes away, right? So light years, light minutes, this is a measure of the distance. Okay, what about the next, the closest star? The closest star, which is called Proxima Centauri, we say it is 4 light years away, right? So with a car, you take 30 million years, with an airplane, 2 million, but the light takes 4 years to get to the star from the Earth. Now we move to larger distances, and to cross once the Milky Way, the light needs about 100,000 years, right? So we say the diameter of the Milky Way is 100,000 light years. So these are much larger distances than these 4 light years or 8 light minutes to the sun, right? We go now to even larger objects, and these are galaxy clusters. So these are large, these are objects where every point or dot, extended object that you see here are individual galaxies. And these galaxies, as we will see, are bound together. But for now, this coma cluster is at a distance of about 3 million light years, and the diameter, so it takes the light 1 million years to cross this cluster of galaxies once. Now we can map the so-called visible universe in many different wavelengths, right? So we learn about these images that you have seen about these objects by looking not only here in the visible light, so the wavelength that is where our eye is sensitive to, but also in the much longer wavelength like radio wavelength, microwave, infrared, or shorter wavelengths, meaning higher energy. For instance, high energy, we call them gamma rays or X-rays. The point here is that these are all wavelengths of electromagnetic radiation, right? Or light, if you want. And we have telescopes that operate with all these different kinds of wavelengths, so not only with the visible. So we learn a lot about the universe, but also about our Milky Way. So this is just, if you look towards the galactic plane, we are used to this visible light, but here you can see it in radio wavelengths or infrared, or here in high energy gamma rays. And actually, I'm not showing this here, but there is also now a picture of this plane in neutrinos. But these are very, very high energy neutrinos. So of course, now the question is that we are asking ourselves: is visible matter the dominant form of matter in the universe? So visible means matter that can emit or can absorb light or electromagnetic radiation. And well, you already know the answer, because otherwise I wouldn't be here speaking, that this is not the case, right? So it turns out that based on many observations over almost 100 years now, we will come to that, we know that when we speak of the matter content of our universe, actually 85%, so the majority is non-luminous or dark. That means it doesn't shine directly, right? And we know this from very different measurements over a different time scale. So from the earlier moments of our universe with a cosmic microwave background to very late times, from the scale of galaxies to the much larger scales of clusters of galaxies, but even to these largest scales that we can observe. And we call these large scale structures. So every single dot here is one galaxy. And on these larger scales, you see this kind of filament-like structure, kind of this, what is called cosmic web, okay? And if you go then even larger scales, the universe is pretty uniform. But again, let's go one step back. And how do we know all this, right? So there was this famous English physicist, Isaac Newton, and about 300 years ago, he managed to explain the movement of the planets around the sun, right? So he came up with this universal gravitation law that's pretty simple, that the force is proportional to the mass of the objects divided by the square of the distance. So the basic thing here is that two bodies with mass attract one another. And this law is universal in the sense it doesn't matter if you talk about the attraction between sun and earth, earth and moon, earth and a soccer ball, and so on. Everything attracts one another, right? By gravitation. And with this simple law, back then he could explain, for example, he could calculate the shape and the times of the orbits around the planets. The orbits of the planets around the sun, right? And for example, he could predict why Earth needs 1 year, per definition, of course, to go once around the sun, while Mars needs almost 2 years, right? So if you look here, this is the orbital speed versus the mean distance from the sun, right? We call this Keplerian motion. So the further you go out, the lower this orbital speed, right? So Mars is further away from the sun, the orbit is longer, the movement is slower, so it takes longer to go once around the sun. Now, almost, so 99.98% of the total mass in the solar system is in the sun, because the sun is so much heavier than the other planets, right? So the point is now that we expect this kind of motion not only in the solar system, but as we will see, also in galaxies. And the gravitation is also what keeps the stars, of course, on their orbits, right? So we have here again the Milky Way. We can imagine now the sun going around the galactic center, and this is something that's measured. It takes the sun about 250 million years to go once around the galactic center. And the sun, and together with us now, of course, we move together with the sun about 220 kilometers per second, right? And we say one galactic year is then 200 million Earth years, right? So this came up in the 70s. There was a physicist and observer, Vera Rubin, also Kent Ford and their teams. They were able to measure the so-called galactic rotation curve. So similar to the solar system, they could measure the speed of motion of stars and also of the gas around the centers of galaxies as a function of the distance, right? So what they expected, because that most of the mass, this is what was believed back then, most of the mass in galaxies is concentrated here in the luminous parts. So they believed that as you go out, further and further out, these rotation curves should also get, the velocities should get smaller. But this is not what they observed. They observed the so-called flat rotation curves actually as far out as one can measure. And they realized that you need about 10 times more mass than this visible mass in the stars and the gas in the galaxies to keep everything together. Otherwise, these galaxies wouldn't be bound objects, but these objects would simply fly apart, okay? And in fact, the story started even earlier. So that's why I said almost 100 years ago with this Swiss-American astronomer, Fritz Zwicky. Here he was at Caltech. So he studied the motion not of stars in galaxies, but of galaxies, for example, in this rich coma cluster that has more than 1,000 galaxies. And here as well, he found out that the speed of the individual galaxies were far too high and they would simply fly apart. So he posited back then that there is about 10 times more matter than in the visible part of the clusters. And he called this dark matter, dunkle materie. He published this in Helvetica Physica Acta, 1933. So there must be some new form of matter that you can imagine it sort of like a glue, right? You don't see it directly, but it keeps this swarm of galaxies together. It keeps them from just flying apart. So now the question is, of course, how can we make this dark matter visible? Or how can we even infer its properties in space? And this is now related to Einstein, who, also, more than 100 years ago, found out that actually mass distorts space, and then space tells objects how to move. And he realized that everything, planets, satellites, even light, is bent by the presence of mass. And I'm mentioning this here because this is how these days, by measuring this small bending of light, this is, for example, in another very massive cluster of galaxies. This is the Abell cluster. So this is an image from the Hubble Space Telescope. Astrophysicists were able to map out, these blue, this kind of blue fog here, how dark matter is actually distributed in the cluster, because you can't see directly, but you just measure the distortion, the small distortion of light that comes from the galaxies, right? And this is how also on large scales, the dark matter distribution can be mapped. This is another example here, but the point is, if you try to summarize a little bit, dark matter, we know it's there. We know it forms the structures that we observe in the universe, in particular also galaxies. And we know it's there because of its gravitational pull on visible matter. But there is one thing that we don't know, not even after all these years, namely its fundamental nature, right? So what is this new kind of matter made of, right? What is its composition, if you want, at the microscopic scale? We know how it behaves on large scales, but not on microscopic scales. And this is something that connects, you know, the inner, if you want, inner and outer cosmos, right? Cosmology that studies the universe at the larger scales, the origin of the universe, the fate, its form, its content, and so on. You know, the universe at the smaller scale that's studied by particle physics. So in particle physics, we study the fundamental particles and forces, the constituents of matter, and yeah, the interactions between. So I'm mentioning this because you will see we believe that dark matter is actually a new kind of particle that we haven't seen yet, right? And again, we have to ask ourselves first, what is visible matter made of? Visible matter meaning the matter that's familiar to us, right? So everything is made out of, you know, we, planets, people, polenta, whatever is made out of molecules, of atoms. Atoms are made of atomic nuclei and electrons that surround them. Atomic nuclei are made of neutrons and of protons. And finally, neutrons and protons are made of quarks, right? And here on the right side, you see kind of a map of all the elementary particles that we know about today. So elementary meaning, as far as we can measure, they don't have any substructure, right? They're point-like. But again, in physics, nothing is absolute. It's just as far as we can measure today, right? So we have the so-called leptons, we have the quarks, we have here the particles that mediate forces between matter, for instance, the photon, and we have the so-called Higgs boson that was discovered 2012 at CERN, that simply speaking gives mass to the other particles. And we also have here neutrinos. And neutrinos are kind of special particles because unlike all the other ones that you can see here, they also don't interact with light. They do not emit and nor absorb any light, right? And this will become a bit important later on. Now, yeah, one important thing is that none of these particles have the properties to be the dark matter particles. So most of them are actually not stable, but of course, protons and bound neutrons are stable, also electrons, photons, and also neutrinos as far as we know. But for example, the heavier brother of the electron, the muon, decays with a mean lifetime of about 2 microseconds. And the other particles here that you see live even shorter, some of them. Neutrinos would be very, very good candidates for dark matter because they also don't interact with light. But these days, we actually know that neutrinos are too light. They don't have enough mass. And it's another question that we are trying to answer with other kind of experiments. How heavy are neutrinos? We don't know, but we know that they're light, okay? Now, this is not a problem in general, especially for theoretical physicists. So the idea is that dark matter particles could be created here in the early universe together with all the other particles that we know about today. So this is here a very, very brief history of the universe, right? From the earliest time that is called Big Bang to about 10 to the minus 10 seconds when most of the particles that we know about today were formed. So, and you know, then there's some evolution, different stages until structure formation, meaning galaxy formations and today. But without going to the details here, the idea is that dark matter particles were created in this primordial soup together with the other particles, but because of their extremely weak interaction or scattering probability from normal matter, we haven't detected them yet. And this is now from a so-called computer simulation, how this dark matter can be distributed in galaxies. So the visible part of the galaxies that we measure with these particles of light, with photons, it's kind of like the tip of an iceberg, right? So the galaxies are actually much larger than we can directly see, and they are surrounded by these halos. You see the radius here is about 1 million light years by this large halo made of dark matter particles. That's the hypothesis, right? So the summary so far the hypothesis is that dark matter is a new yet undiscovered particle that has to have mass, heavy, no electric charge, and because of that, it cannot emit nor absorb light. That's why it's called, dark or invisible. Now the question is, of course, how can we make these particles, this dark matter, visible? So our method is to look for very, very rare predicted collisions when these dark matter particles come and collide, for instance, with atomic nuclei, with atoms in your detector, right? So you can imagine them like a scattering of 2 billiard balls, but one billiard ball, you can't see it because you're in the dark and it doesn't glow, right? But it's there, it comes in, it has a certain kinetic energy, and this energy, it can transmit part of it onto an atomic nucleus. And this nucleus then can leave a small energy in your detector, as we will see, that you can measure, okay? So it's a collision between, if you want, visible particles and dark matter particles, where some energy is transferred, and this is how we can then make them visible. Now, you don't need to memorize the formula. I just put it here to make clear that we can then calculate based on what we know about the galactic rotation curve, based on some assumptions about the mass of the particle and so on. We can calculate what we would expect in a detector. And from the measured local dark matter density, local means at the location of the sun, of the solar system, right? And this can be measured via this rotation curve of our galaxy. So from the measured dark matter density, we can calculate that we expect about 10 million of these dark matter particles through your hand every second, right? Now, this seems like a very large number, but actually it's not that large, 10 millions per second, because the flux of neutrinos, for instance, is much, much, much higher. And we can measure this local dark matter density with different kind of observatories. For instance, one is the Gaia mission. That's a European mission that measures the precise movement of billions of stars in the Milky Way. Now, of course, we have a problem. So we said we expect about 10 million through the hand or through a detector, whatever, per second. However, there's a flux of cosmic rays. And these cosmic rays are very high energy particles that come from the cosmos, from supernova explosions, also from the sun and so on. And they collide with atoms in the atmosphere, and they produce these showers, as you can see here, showers of energetic particles, gamma rays, electrons, protons, and so on, neutrons. And these will then, these fluxes are much higher than the expected flux of dark matter, right? So we cannot, simply speaking, we cannot build a dark matter detector and put it on the Earth, because what we would measure would be this flux of cosmic rays. The signal we are looking for is much, much smaller. So what do we need to do? We need to go deep underground. So detectors must be constructed in underground laboratories. The deeper, the better, because we then use the Earth or the mountains here as a shield for cosmic rays. So the cosmic rays are mostly, not totally, absorbed by this rock, while dark matter particles, and as we will see also neutrinos, they can simply go through because they have very, very small interaction probability with normal matter. And there's quite a large number of underground laboratories in the world. There's a network of them. But I work in the Gran Sasso lab in Italy that is close to Rome, and it provides about 1,400 meters of shield. So this lab was built in the mid-80s. It has 3 large caverns, and there are different experiments for neutrino physics and also to look for dark matter. So yes, we need this quiet environment to shield from cosmic rays. Maybe you can imagine, like, if you would like to look at the stars on a sunny day, right, when the sun's out, you wouldn't be able to do that. The stars are still there, but you can't see that because the sun provides so much noise. You can only see them at night. And this is similar. We cannot see dark matter at the Earth's surface because of these cosmic rays. And oh yes, this is just the entrance underground lab. This is the surface building. This was in the summer when I brought some equipment there. So this is how this Gran Sasso, it's a very nice region in the Abruzzese mountains in Italy, about 120 kilometers from Rome. And there's a large competition worldwide to detect these dark matter particles. There are many different kinds of detectors. They look either for a small a heat signal, a small charge signal, or a light signal. When such a dark matter particle comes into your detector, collides with an atom and deposits a small amount of energy that you are trying to measure, okay? And I will talk now about our detector. So we use a liquid xenon. For now, we have a detector that has about a total of 9 tons of liquid xenon. So xenon is liquid at minus 100 Celsius. It's a transparent, it's 3 times the density of water. So, and what we do when a particle comes in, we measure a small amount of light. For the physicist, maybe here it's scintillation light. We also look for the small charge signal, so for the few electrons that are produced in the collision by measuring another light signal that comes later on. So from you will see we have a large amount of liquid xenon, and this liquid xenon is then seen by so-called arrays of very, very sensitive photodetectors. We call them the eyes of our detector, and they can measure actually single photons. So we can measure single particles of light and also single electrons in these, almost 9 tons of liquid xenon. So we get the position of the collision, we get the time, we get the energy, and also we get what kind of collision it is with this kind of detectors. Now, this is already a picture of the xenon experiment in Gran Sasso in the underground lab. So this is the service building here. We need to keep the xenon cold, and we need to keep it clean. We constantly purify it. This is all the cryogenic system. This is all, we need to take out the data to analyze it from all of these photosensors. We need to store the liquid xenon when it's not there. So this is about 10 meters high, this building. And this is, what you see here is a large water tank. And we put a picture on top of it, how it looks inside. Because even though we are deep underground, we still need to shield from some of the cosmic rays that can make it to the underground lab. These are muons, the heavier brother of the electrons, but also from radioactivity, from the natural radioactivity of the surrounding, right? So we have a water shield, then we have another shield against neutrons, and then the detector will be here in the middle. So I will just show you some pictures from these shields. So this is just this water shield around the inner part where we keep the xenon. This is then the cryostat here. So we have a large stainless steel, a double cryostat to house the detector and the actual liquid. These are some of the photosensors in the water shield. This is part of the cryogenic system. So I'm showing this picture just to make maybe clear that it's a very complex kind of experiment. And of course, we didn't start with 9 tons of liquid xenon. We started, quite some years ago with 10 kilograms. Then we moved to a 170 kilogram detector. Then we had a 1 ton, and now we are operating this almost 9 ton. And in Zurich, we were mostly working on the inner detector. We call it time projection chamber, just because we can measure the time, the energy, all of these quantities. And this is about 1.5 meter high, 1.3 meter diameter. And you can see here, we have about 500 of these very sensitive photosensors that we developed together with a company in Japan, with Hamamatsu. And these photosensors have very low reactivity and can measure individual particles of light. And this is so this is all installed in clean rooms under very clean conditions and so on. And you can see here me and also my colleague from Colombia. This was with a previous detector that was still smaller, the ton scale detector, 1 ton. Yes, this you can see here again, also what we call the eyes of the detector. So these very sensitive photosensors that measure the UV light that is emitted in a liquid xenon detector. I think I don't have a lot of time, so I will say that we started with this detector, the dark matter search, already in the spring of 2022. The data is being analyzed. This here is calibration data, but this is how this background noise looks like, and this is how a signal from dark matter would look like. So we expect, at least from some dark matter candidates, we expect to see these nuclear recoils. And what we call here electronic recoils are interactions with the electrons. Okay. Now, yes, it was mentioned a bit at the beginning or before we actually started. So we haven't seen the dark matter particles yet. We hope we will be able to detect them. We don't know, of course. But this year we actually measured for the first time with this xenon anton detector neutrinos from the sun. So this is a reaction that has never been measured before with solar neutrinos, and it's called coherent neutrino nucleoscatters. So very few scatters of these neutrinos that are emitted in a certain, so neutrinos, solar neutrinos come from fusion reactions in the sun. Our sun shines by fusing protons to helium nuclei, and what we see are the photons that come from the surface of the sun, right? But neutrinos really come from the core, from this fusion, from this nuclear reactor. So by looking at these neutrinos, you can also basically look at the core of the sun. So on the one hand side, these neutrinos are the ultimate noise background for the dark matter search. That's why it's called neutrino fog, right? Because you cannot shield neutrinos. But on the other hand, they are also interesting signals in their own right. So we hope with these measurements that will be refined in the future to actually learn more about neutrinos themselves, but also to learn more about our sun. And I was quite happy to see that this news made it to the highlights of the year for the physics magazine. So they have these 10 highlights, and this was this neutrino fog, as they call it, rolling into sight, was one of these highlights. So we are not stopping here, as it was said. Darwin was mentioned. Actually, now we are even larger. So the Darwin collaboration, we joined forces with our competition. It's called the Lux Zeppelin experiment in the US and UK. So we are called now XLZD. So this comes from Xenon, Lux Zeppelin, and Darwin. And the goal is to build a larger detector, not only 50 tons, but about 75 tons of liquid xenon in total. And yes, it was mentioned this xenoscope. So we are doing research and development. And we study, for instance, a very long type of time projection chamber to study the drift of electrons and many other properties at this scale. But we're also working on next generation photodetectors, so to improve the yes, the collection, but also the detection of these very few photons that are emitted. And this is all to increase the sensitivity of this, what we call next generation detector. You can see here some of the people in my group, and when we built this very long 2.6 meter tall TPC that actually now we already had some data last year, and we plan to run again next year. It was also said that we are not only looking for dark matter, but with this next generation detector, we want to look for solar neutrinos. We hope to see neutrinos from supernova explosion, also atmospheric neutrinos, and we would like to measure, if you want, how heavy neutrinos actually are. So it's more like a broader observatory in astroparticle physics. Now, going back to dark matter, there's still many questions that are open, right? So first of all, is dark matter really made of this kind of new particles that have mass and are weakly interacting? This is a very good hypothesis, but we have to show that it's true. We have to show that we can see these particles in the lab. And once we detect them, the next questions open up. What are the properties? What is the interaction rate? What is the mass? And so on. What else can we learn about these particles? And who says it's only one type of dark matter particle? The visible matter is also made of different kinds of particles. And maybe there's an entire, what is called dark sector out there. So maybe there's more than one dark matter particle species, more than one species, right? And then finally, also, what is the detailed distribution of these dark matter particles in the Milky Way? So I will leave you with these words. These were said in a different context, in the context of looking for exoplanets back then. Namely, the probability of success is difficult to estimate, but if we never search, the chance of success is 0, right? People always ask me, well, you have been looking for dark matter for 20 years now. When will you find it? Will you see it next year? And I cannot say. I don't know. It depends on the properties of the dark matter. So this probability is really difficult to estimate. But what I know is that if we don't look for it, for sure, we will not find it, right? And I realized, actually, that some years ago, I wrote a more general article about dark matter for the Academia Europaea in this European review. So I put the title here in case you want to read a little bit more, in case you're interested. So thank you very much.
Well, thank you very much. It was a very, very interesting lecture. I let you speak 3 minutes more because it would be a pity not to listen to the end. I'm sure that we will have many, many questions. But first, Violeta, please present the next speaker.
Thank you also so much, Laura, for this fascinating lecture. I am very happy to present Maria Miraglia. She is an Italian poet, essayist, translator, and peace activist. She graduated in foreign languages and literature at the University of Bari. She holds later multiple master's degrees, including one for the University Aldo Moro in Bari and another in modular didactics in Rome, Tre University. Among many professional activities, she achieved merit certifications at Trinity College in Edinburgh and the International House in London. Maria Miraglia was a member of Amnesty International and later joined the International Observatory for Human Rights. She is the vice president of the World Movement for the Defense of Children in Kenya and founder of the World Peace Foundation. Maria Miraglia's influence on contemporary literature is profound. She is a founding member and literary director of the Pablo Neruda Association, a member of several World Writers Associations, honorary member of Naciones Unidas de las Letras in Bolivia, co-editor of Contemporary Vibes, India, and a member of several editorial boards of international magazines. She writes in Italian, English, or both languages. Her poems have been translated into over 30 foreign languages. They are prominent in more than 100 international anthologies and magazines, and received numerous national and international prizes and awards worldwide. The work that made her known to a broad audience is Dancing Winds, which has also been translated into the Telugu language. Her literary works have been featured in various international publications, and she is recognized for her contribution in poetry and peace advocacy. I'm very happy to invite Maria Miraglia.
Thank you. Thank you. We are going to put on the slides. Okay.
Would you like to share a screen?
Yes,
It's
yes.
possible, just to...
I am going to
Great.
do it.
Okay, it's done.
Okay. Well, the previous speaker has talked about the sky and has illustrated a long travel through the stars. I will try with my sheets to talk of the inside universe of female poets. Well, I begin talking about poetry. Poetry, which has a very ancient origin. It dates back to prehistoric times with the hunting poetry in Africa, where some of the earliest poetry were found in the pyramid texts written during the 25th century before Christ. As to the Eurasian continent, the first form of poetry was folk music, and it comes from the need of a man to retell epic stories, while the panegyric and elegiac poetry were typical of the Niger, and the Volta valleys. The poet received inspiration from the Muses, who were daughters of Zeus and of Mnemosyne, the goddess of memory. And the writing, as we know, was still unknown in ancient times. And the poet needed to learn everything by heart in times in which, in times and society in which culture was only based on oral transmission. And this is why the Canadian cognitive scientist Steven Pinker argues that literature has an ethical power in what it shapes the human being and souls. Moral, all norms, from moral, religious, social norms, were all formulated in verses. This because their musicality could help memorization, such as music. And in ancient Greece, even laws were sung. And it can't surprise if these verses, laws, were not written with an imperative form, which was adopted from the Roman times onwards. The instrument which accompanied poetry were the lute, the flute, the druid harp of the Celts. Only after the invention of writing, poetry, and music differentiated. As to the European continent, the union between the two forms of art lasted till after the 13th century, when poetry became a cultural phenomenon and lived a life for its own. And it only united sometimes to music, but only to a cultural form of music, the madrigal. During the time, we know that authors had a larger space for them. I mean, male writers, male poets. We know a lot of their names. We know so many of their works, verses. But women, even if they tried sometime to express the motion of their souls, of their heart, they were never mentioned in school programs, nor in anthologies. Also, in ancient time, women have had no chance to access education. They were relegated only to domestic schools, and their function were to be housewife, mothers, nuns, courtesan, or cartsen, I say. And just only some young girls belonging to noble families received a certain kind of education. In particular, they could have some knowledge about poetry and music, which they had to left soon after they got married. This can be attributed to the fact that along old medieval era, there was a misogynistic vision of life, which was due to the presence of Aristotelian writings. Aristotle, in his Politics, for example, argues that women were inferior to men, that if the virtue of a man consisted in commanding, the virtue of a woman was in obeying. And he also added that one more virtue for a woman was silence. She had to keep silent and obey. Greek philosophy influenced them. Can you hear me? Yes. Greek philosophy influenced a lot also the Christianity. And so also the Christian church thought that women were inferior. So, I hear my
There is
voice.
an echo.
Somebody has, please make yourself silent. Turn the microphones off.
Okay. Okay.
If you are the host, you can also do it.
Okay. So I
I'm
was
not Violeta, maybe can do that.
I was talking about Aristotle, and was saying that he influenced the Christian church with his thought. So also Christianity thought that women were inferior to men by nature. And Plato, in his Republic, says the contrary. He says that the women have the same rights of men, and that they have the identical right to education in any field of, in any cultural fields. He emphasizes that there is no substantial difference between men and women. So we have to wait so many centuries before this kind of idea can get its space and see much more women in literature. But it can be surprising what I'm going to say now. That is that the first poet in the history of humanity was a female whose name is Enduana. It is also true that she was not a girl like many others. She was the daughter of the Akkadian king Sargon, who lived about the 24th century before Christ. So from the Mesopotamia history, she emerged as a woman of strong personality who covered not only the role of a princess, but also the role of a poet and a priestess, because once she reached the age of adulthood, she was consecrated to Nana, who was the god of moon, and so becoming the link between the divinity and man. One of her most important writing is Lady of All Me, which is a poetic composition of 153 verses, in which Enduana tells about the escape of the temple of Ur, her exile following the usurpation of her father's kingdom by the last Sumerian king. But also she expresses her fragilities and her weaknesses as a woman. Much more after having witnessing the earthquake of her town. It is not clear who was Enduana Mothers, because she wrote with a great elegance in Sumerian, while her mother spoke Akkadian. Maybe she was one of Sargon's many concubines. But what is remembered is we are talking of 25 century ago, and the first person who signed a poetic collection was not a man, but it was a woman. Talking of a poet, we can't forget to remember Sappho. Sappho, who lived in the 6th century before Christ. So a lot of centuries have gone from Enduana and Sappho. She was born on Ereso, on the island of Lesbos, but lived mainly in a bigger town whose name is Militene, and probably she came to Italy, in the south of Italy, and lived for some time in Syracuse for political reason. The age in which she lived was one in which women had a relatively marginal role in society. And for example, they didn't enjoy political rights. And if they had to go out of their homes, they were usually they needed to have a maid with them. But Sappho was a great woman. She dedicated herself to the education of young women in a sort of intellectual cenacle, which was called Thaiasos, where women received a global education. Mainly, they knew big poetry and something about music, but they were also educated in marriage life, which also included sexuality. And in the Thaiasos, relationship between Sappho and these young girls often took on a romantic or sexual connotations, of which Sappho talks in her poems, which are both monodic and choral. So she's remembered for being one of the first poet to talk of a non-heterosexual love. And till nowadays, she's remembered as one of the poets who best wrote about love. She declined in various ways. Her lyrics were gathered after her death by the Alexandrian grammarians and collected in 9 volumes. But I can't say the poet, but I can say the women, the philosopher of ancient time, who represent much better than any others, can illustrate, can highlight which was the life of women during all the medieval ages and also beyond, is Hypatia. Hypatia lived in Alexandria in Egypt, and she received a first-rate education from her father. Her father was a mathematician, an astronomer, and the director of the museum. She also furthered her education in Athens and in Italy. But above all, at the Neoplatonic school. When she was 31, she was a handsome woman and a wise woman, but she never married. And despite the widespread Aristotelian misogyny, she became an authority. I'm sorry. She became an authority, and a lot of people came from anywhere to listen to her lessons. But she reached a great fame, but her end was terrible, because the then bishop of Alexandria, who was persecuting the heretics, that's the followers of the Hellenistic Neoplatonic school, decided to kill her. So Hypatia was brutally murdered. She was attacked in the street, naked, dragged into the cathedral church, and while still breathing, her eyes were gouged out. So she's nowadays remembered as being one of the first beach hunt by the Christian Church, by the Inquisition, the Christian Inquisition. I would underline something by this woman and maybe explain why I choose her instead of other many authors of the time, because she taught not only the things in which she was an expert, but she also taught to protect the protection of minorities, the separation of spiritual power from secular power, all things which are still today discussed and are not still lived as we could nowadays after so many centuries. One of the most, I have to, yes, Sappho. This is a Sappho. I turned the page now. Now I go on. I talked of Hypatia. I hope you can see now the images. The moment in which she was massacred in the street, and on the other side is Cyril, the patriarch, the Catholic patriarch who ordered her assassination. Now we move from Greece to the 5th century, the Italian 5th century, and we are in Florence between between the 12th century and the 13th century. Compiuta donzella was a name widespread at the moment, which translated into English means a young lady of great virtue. And I can't say if this is a real name or just a pen name. What I can say is that her poems were well known at her time, and that poets like Guittone d'Arezzo or Guido Guidizelli admired her poems. She wrote a few poems, but all her writings were enclosed in the Vatican Code number 3793. And she's remembered for being the first woman who wrote in Italian vernacular. Is the first thing we remember about this young poet who lived her life at 24, very, very young. Now we go from Florence, from Italy, we move to France to talk about Christine de Pizan. She was, yes, I am slow in moving my pages. Now I am on the right one, I suppose. Yes, Christine de Pizan lived in France, but she was of Venetian origin. And because her father was appointed by Charles V of France as astrologer. And she lived there with her mother and all her family, receiving a very good education from her father, much more than her mother. At the time, still women were not considered as possible women of culture, but were considered and seen as housewives. After, when she was 15, she was given an husband who died sometime after, and Christine found herself in economic difficulties. In times in which women were considered a creature to be protected, she was able to become the first professional woman to write. And she was an historian, an editor, and was one of the first women to live on her work. Who rejected the misogynic vision of women so widespread in her time. She wrote on demand. She wrote a lot of books, La Cité des Dames, and criticized Le Roman de la Rose, in which women were seen as second species human beings. We reach we can reach now the Renaissance time, when women poet at last had their space and had the chance to express their ideas, to let people hear their thoughts. The Renaissance was first centered in Florence, from where it spread all over Europe, and the two most important names we remember of this time is Vittoria Colonna, and Isabella Morra. Vittoria Colonna was born in the most important Roman family and was promised still young, as it was usual at that time, to Ferdinando d'Avalos when they were still children. The marriage was a happy one, but her husband died, and Vittoria Colonna left alone, and she fell into depression and also attempted suicide. The theme around which she wrote were love and spirituality. She never published. Her poems only circulated in Rome among the cultured people of the time, in a particular way, Michelangelo Buonarroti, who was a close friend to Vittoria Colonna. And he wrote something when she died. When she was the source of all my sins, flied from the world, herself my straining sight, nature, who gave us the unique delight, was sunk in shame, and we had weeping eyes. Colonna was very close to the Pope Clement VII and to all the major figures of her time. She was one of the most fascinating figure of the Italian Renaissance. Okay, we have to change. Okay. This is the painting of Colonna, of these Roman women belonging to one of the most important Roman family. And you can observe her deathbed with Michelangelo at her side. Oh, well. Now, I can say something about a woman who had not an happy life. She was born in Favale from a noble family. And as a child, he also received a good education by her father in a first moment, and soon after from a tutor. Her father was compelled to leave for France for political reason, because he had decided the king of France instead of the king of Naples. So Christine grew up together with a helpless mother and some rude brothers, who forced her to live in a complete isolation. And when they discovered a liaison with a duke of a near castle, they decided to kill both her sister and the Duke d'Avalos, who they supposed was her sister lover. So the first to be killed was Isabella Tudor, sorry, Isabella Morra. The name of the poetess is Isabella Morra, and killed her tutor because he was accused to have brought letters from between the two lovers. This was then soon after, they killed her daughter and left for France. As they returned, also Isabella lover was killed. And unlike Isabella wrote some poems who celebrated love and were discovered at the moment in which the authorities entered her castle to take notice about the assassination of Isabella. Okay. I can say something about the Arcadia. Was very important in an academy, a literary academy, which was born in Italy, in Florence, but that widespread all over Europe. It was due to the Queen Maria Christine of Sweden, who came to Italy after her conversion to Christianity, and she gathered around her a certain number of literary men. Soon after her death, two of these men founded an academy in which for the first time women had their access. And in this academy, whose name is Arcadia, about 450 women had access. Among these women, there were Maria Luisa Cicci, who was a very young girl, educated by her father. Soon after the death of her mother, when her mother died, she was only 2. And her father, when Maria Luisa reached the age of 8, as usually happened, to tell the truth, between the 12th and 13th century, was entered a college kept by nuns, and her father was a man of law, asked the nuns of this college not to give education to her daughter, because at the time the daughter were educated to virtues, just to virtues, because they were a human being, were destined to get married, and it was thought there was no need for them to be educated, to have to receive any culture.
Maria, it is very late.
You're right. I'm so sorry. I am so sorry. You're right. There is so much to say about women in poetry. And I would just add one thing, that women were excluded from poetry, from literature. And they just succeeded to enter this field about the end of the last century. So it is very late, their presence in poetry and in literature. This is all. It is a long story. I succeeded to tell something, and it is enough.
It's in Arcadia ego.
Yes.
Thank you so much.
I wish just to add that Arcadia was the first time in which women had the chance to be poets, to write, to be listened and to be read.
Thank you so much, so much. Dušan, please, you begin now.
Yes, I don't see any hands still, but I'm sure there'll be many questions.
Yes.
And, yes, okay. Please, Maria de la Chiara.
Ioannis and Maria Luisa. Yeah. Ioannis, I think it was. Yeah.
Is the first? Who is the first?
Yeah,
Am I
you.
first or
I
second?
saw
Okay, yes,
ladies
you.
first.
Ladies first.
No, I have a question to the first speaker. Her presentation has been really extremely interesting and also very, very clear. I have only a theoretic curiosity, perhaps it is somewhat naive. The curiosity is the following. Which theory of contemporary physics is particularly important in these fascinating researches about dark matter? For instance, to what extent is Einstein's general relativity important? What is the role of possible quantum effect? And perhaps is there any possible application of a present quantum gravity theory?
Yes, thank you. So yes, so there are quite a few questions. Right. So in terms of Einstein's theory of relativity, yes, it is still very important because it's something that I did not mention, but there were also attempts, and there still are, of course, because to say, what if we don't understand gravity? What if gravity is modified at other distance? Right? These are called modified theories of gravity. So this was tried also over many decades, but so far without success, actually. And also the Einstein theory of general relativity seems still to be correct as far as we can measure. For example, one prediction of these alternative theories of gravity was for dark matter was that if we detect gravitational waves and at the same time from an object, if you also detect the light, then these should move at different speeds, right? Einstein predicted that gravitational waves, so these are really, if you want, ripples in the fabric of space-time, that this should also move with the speed of light. And when this was detected, there was, I think maybe 2017, a collision of two neutron stars where both gravitational waves, but also other, optical signals, if you want, were detected, then it could be measured that actually true gravitational waves move with the speed of light. And an entire series of these alternative theories of gravities could be ruled out. So as far as we can measure, yes, because all of what I've mentioned, of course, is also on the basis of Einstein's theory of relativity. Now, in terms of particle physics theories, there are quite a few. So we have the standard model of particle physics with these, interactions and matter particles that we know, and there are different theories that extend the so-called standard model, and some of these, or many of these, actually also predict new particles which can be dark matter candidates, right? And quantum effects always play a role because everything. At the subatomic level or even atomic level is quantum in that sense, right? Now, quantum theory of gravity, this is really only important in very, very early moments of the Big Bang or in the interior of black holes, right? So that's still something that, it's not, we don't have we don't have a quantum theory of gravity or so, right? So, but this is not so relevant for the universe as it is now at large scales on galaxies. It's really in very extreme conditions, right? So very dense matter, very early moments. Yes. However, there are quite a lot of developments for new type of quantum sensors, as they're called, right? You know, relevant to be quantum computers and so on. And these are now more and more used also perhaps to detect these dark matter particles. We also have a small experiment here at the University of Zurich that we started. It's actually called Crocodile with Q from Quantum, where we use new type of quantum sensors. So maybe, I don't know if there are some physicists here, but these are superconducting nanowires, where we also try to detect dark matter particles, but very, very light dark matter particles, for example. So yeah, so this is relevant, and I don't know if I answered your question.
Maybe Ioannis will ask you something that you can add to the
Yes.
first question.
Thank you. Yeah.
Thank you.
Yeah, actually, I would like to start first with, I noticed, Laura, that you have published in the Journal of Academia Europaea. Well, I would like to tell you, probably Dušan, Šuput, and Violeta will give you details. We have our own proceedings of the European Academy of Sciences, managed by the Page Press in Italy, and I invite you and Maria both to submit your talk as a review in our journal. Actually, in chat of the present Zoom, I have sent the link. Maria knows about EASA. And by the way, also, Maria mentioned about Hypatia. Well, I have read a lot about Hypatia. There is an International Day for Hypatia Day of 15th of March, just for information.
Nice.
Now,
yes.
Dear Laura, I enjoyed your beautifully presented overview in a, I could say, understandable way. Where in the infancy stage to comprehend, as we know, our universe, and crawling, we try to reach the state of the art that you briefly presented. But what is your opinion of the Big Bang? Is an explosion of one bubble out of many, and not only one? I mean, having many small bangs. The physical laws apply to our cosmos, okay, to our cosmic bubble. But what about outside? There could be another universe with other laws. Just, I would like to know your opinion.
Right. So exactly. So what we call, of course, Big Bang is actually not even the earliest moment in the universe, what we call the hot Big Bang. But the question is, I think the question that you ask is, you know, it could be that we are one bubble in a much larger landscape of universes. So there are parts of the larger, you know, what we talk now about is the observable universe. But the question is, what is beyond this observable universe? Are there other pockets of space where also space-time expands, or maybe others where space-time, you know, because it depends on the matter and energy content, what happens, right? And you know, are there other bubbles where you have this, what is called the Big Crunch, and so on? Now, the fact that, and there are many different kinds of multiverses, if you want, right? So these are allowed by the laws of, you know, by mass, by the laws of physics, right? It's allowed. The problem is that so far we don't have any means to really, how to say, to verify this kind of hypothesis by observation, right? Because you can have, of course, you can have, so the different type of multiverses, but you know, the theory of inflation and others, they predict that we are just one bubble in this multitude of bubbles, and that's something that unfortunately we cannot verify, but you can also not. So it's at this point it's more of a philosophical question, right? Because you know, you would like to have a theory, you would like to have to test it, and then perhaps you need to modify it, and so on. This is how empirical laws, empirical theories are, you know, that's how we proceed. But sometimes you have predictions that are consistent, with all the laws of physics, the law of math, but we have no means of verifying those, at least not yet, right? So in that sense, my opinion, you know, you can have a preference for or against, but it doesn't matter actually so much unless you can really test it, right?
Yeah.
But yes, I think, you know,
I think Peter Hermann has a question as well. I don't know who. Please ask in all directions. In all directions.
It's actually a question to both of you. Can we still operate with the terms we have? And you said actually we try to we don't have the means. And do we have actually the terms? And that's this, to you the question, but as well to Maria. If we look at the position of women, we see that we are again and again struggling and using certain terminologies, for instance, in law, but there is no progress, because if we apply simply law, we fall short of finding a solution. And there is, for instance, in Sweden, a very good law in terms of equal opportunities, but again, we fail that it is actually implemented. So I'm wondering if we are in general in science now, in arts as well, at a breaking point where we simply have to rethink our basic concepts to move on. Quantum physics is one part where actually we come often to this conclusion, gravity as such doesn't exist.
No.
I once heard one of these experts saying gravity doesn't exist, but still, if the cup falls on the ground, it breaks.
Well, it's maybe some, you know, some news line. I will let Maria answer, but these kind of headlines are sometimes they attract clicks, right? But doesn't mean much. But yeah.
I would say that many things have been done for women, but our life, female way of living their life was dictated by ancient philosophy, and to which also the Christian Church aggregated. So women had to work a lot to try to find their space in life. I am a poet. I talk with a female poet, and still today they have some difficulties. When I meet, when I have some meeting, some events where I present my books, many women asks me, how have you done? Where did you find your time to write, to publish? So something have been done in social life to help women that I consider the second half of the world. Like Plato, I follow Plato philosophy, not Aristotle. So when all the people will begin thinking that women and men are the same. Plato says that both male and female human being can have the same soul. Soul have no gender. So why and that also Plato says that we can have many lives, such as the Indian says, the Indian psychology believes in reincarnation and metempsychosis. And some old psychologists of the ancient times taught us that there is no difference in souls. So a soul can enter a male body or can enter into a female body. So why make differences? Why? And still today, in Italy, we have about an uxoricide every 2 days. A woman dies in Italy every 2-3 days because of her husband, because of her mate, because it is not accepted equality between the two sexes. But I am sure, I am talking of Italy, but I am sure it is not a problem of Italy. It is a common problem. Think of the south of the world, because I have a journal line with about 20,000 members, mainly from the southern countries of the globe. It is terrible what happens in. Think of the last countries. Even in Persia, in India. In India, oh my God, I had been in India, I had been in China. There is a very different way of living, a very different consideration between of women in this country. And if we just have our problems as women who wishes to give their contribution to society, because if the friend who was talked before is an excellent scientist, she's a woman, but she can give a great contribution to society. Why we have to miss all this? Why?
Yeah.
So yeah, in science, just to say, I think that's very interesting. And of course, in science, in physics, it's there's no
In
much
every
difference.
field.
It's very
In every
different.
field.
It's very similar, right? So just an example, right, where I came in Zurich, my husband is also a professor of bioinformatics, but people ask me, how do you manage to do this? You have 2 children. How do you manage to be a professor? But nobody is asking my husband, how does he manage? He also has 2 children and so on, right? I asked you, but why don't you ask him how he manages? Because so it's always this. Even
our problem. This
even
is
today.
still our problem.
Yeah, yeah.
Because if a woman has a particular valor, soon she's asked because of your husband. It is because of your husband. It is because of your husband. I taught in schools and I had to fight to show my worth, because men were just considered better than women in any social environment is so. So we had our freedoms, but we have to go on. I had a meeting with a special person talking about women, about their worth in society, but there are the women who don't believe they can do. It is women that don't believe they can go, they can fly high.
Yeah, but I think it's even worse, because I saw in schools with my school with my grandchildren, teachers, female teachers, prefer male pupils as they are better. You know, they are in their eyes, in women eyes, they are better. So that's also one of the problems. And I think that if you go to more intellectual society, you have less problems between women and men position. But still, I think let's say with my wife, I see that expectations from women were always much higher to work in the family. And I saw, let's say, with my PhD students, there are some brilliant students that after PhD in a year or two, they just disappear from science. So that's quite sad to see. But if I go to the question about multiverse and so on, of course, it's very hard to detect something, even neutrinos we cannot detect. So how could we detect something else if it exists? And even, let's say, how do you handle thermal noise? You get from devices that you use for measurement, you get noise. How do you make sure that it's what you measure?
Aha, yeah, right. Well, that's a long discussion. So there's no, well, noise depends how you define it, right? Do you mean noise in our photosensors, in the photomultipliers? There, yes, the rate of what we call dark counts, if you want, right? So that rate is actually pretty low, but we always monitor it. So yes, liquid xenon is cold, it's -100 Celsius, but it's not very cold, right? It's much warmer, if you want, than liquid argon. So there is some thermal noise in those sensors, but it's much, the rate is so low that it doesn't affect our signals above our energy threshold. But, it's always, of course, it's not zero, right? So it always determines this noise somehow, the threshold, our energy threshold means the sensitivity to certain kind of interactions, right?
Excuse me, you mean noise, but there is a pitch also? I mean, a pitch?
Not
There
really
is
in that sense.
no noise if it's a pitch.
Noise right, not in the, yeah, exactly. You could, yeah, there are artists actually who would translate what our detectors or other detectors measures into sound, into music. But this is more, in this sense, it's noise that you see some signals in your photodetectors that do not come from actual physical particle interactions,
The
but
difference,
are
excuse
due
me,
to
the difference between noise and sound
right,
itself
right.
is the question of frequency. If the frequency or not frequency. So that's a noise never have a pitch.
Violeta, I think
you cannot identify a pitch.
in science, noise can go to frequencies where we don't even imagine, with about hearing or seeing. So I think thermal noise is, I don't know what would be the frequency, but I'm not sure. I think we could hear some, maybe not in your case, but
in our case, this noise, it is a frequency of hertz or so,
Okay,
yeah,
the
tens
other
of
thing
hertz.
is, I was shocked by the image you showed about universe as a network. It was like looking at brain. Exactly. When I saw, immediately I got the impression that I'm looking at histology of brain, but it was
right, because you have these filaments. However, right, you have these filaments. You have this cluster of galaxies, and then you have the superclusters, right? So these are groups of clusters of galaxies, and then you have these filaments in between. But then, if you go to even larger scales, you get kind of a more uniform picture. And yes, and this is thought that it has to do with quantum fluctuations in the early universe, which were then amplified, as the universe grew and expanded, which were amplified also because of the presence of dark matter to these, to build these, very large structures then on the cosmic scales, right? So you start with this very compact universe, right? You start with quantum fluctuations, and then the universe, space-time itself, right, expands, cools down, and these quantum fluctuations are the seeds of structure formation, right? And we know this because we also see, I didn't really go into this, but we see, I only showed the picture of the cosmic microwave background. What does it mean? This is this radiation that comes from all directions on the sky. And this was emitted about 400,000 years after Big Bang, when the universe first became transparent. So this was the time when electrons and hydrogen nuclei, protons, formed atoms. And then the photons, the particles of light, could escape, because before that you had kind of a soup, right? The universe was so dense and so hot that you had all the time scatters between electrons, protons, photons, and so on. But when at some point the universe was cooler, so electrons and protons could form hydrogen atoms, and then the photons could escape, right? And they reach us still today via this, but today, of course, the temperature of these photons is very low. It's about 2.7 degrees Kelvin, so 2.7 degrees above absolute zero. And this cosmic microwave background, was one of the pillars of the theory of Big Bang, right? And this was discovered first by Arno and Penzias in 1965, right? There was a Nobel Prize, and then it was measured much, much better later. So there were several Nobel Prizes because of this cosmic microwave background, but the latest measurement we have from an EASA satellite, from the Planck experiment. And why is this so important now? Because these very small differences that we can see in the temperature of the sky, this point back to these initial seeds, right, of structure formation, and also tell us how these large-scale structures, these filaments and this web formed later on.
Yeah, I think it's, things like astrophysics make so much imagination, like multiverse, there's only one, or now when I saw this picture of like brain, maybe we have a common soul, as we heard
Right,
in the other lecture.
but we have to make a difference between some theories that, some possibles, while with other things that we actually measure, that we know the physics that was tested in the lab and so on, right?
Yeah, sure.
Like,
sure.
yeah,
Is there any other question? You
Ioannis
want
has
to ask again? Okay,
Ioannis.
Ioannis would like to ask again.
Yeah, one question for both of the speakers, because I would like to bring you, the participants and all of us to the level of coupling between the first speaker and the second speaker. So a question which I had made long time ago to my dear teacher, late Professor Peter Higgs in Edinburgh. So what is first, both of you, your reflection, if beyond any particles or neutrinos, is lying the ideas, much like Platonic ideas in his myth of cave, as you know. A poetical outbreak, for example, could express such ideas. It could be a catchy phenomenon of a cosmic, I would say, archetype, which has been imprinted into the human Jungian archetype. I would like to know your opinion about this.
So maybe I'll let Maria speak first as the poet.
Yeah. I think that Plato represents the noblest thought ever expressed, according to me, because he makes no differences between the genders. So people along the time, there have been a lot of phases in which it was necessary a certain kind of life. But Plato is a philosopher since a long time, has expressed his clear opinion about individuals. And if he thinks that soul has no gender, and that soul can enter a body, a male body or a female body, where is the difference? There should be no difference between the genders, the two genders.
Yes, what I ask is beyond the material and the matter is ideas, like the Platonic ideas in the myth of the cave, nothing to do with male or female, but an poetical outbreak.
Yes.
So such a poetical outbreak, but what? To catch something, which is back, in time, a cosmic archetype.
Right, but what you're saying, to have
has
ideas
been transmitted on the human one. That's
right, but to have these ideas, you need a human brain, right? So there was a certain evolution,
of course,
even across, from, I mean,
of course, that's why I would like to have a reflection, like we are living in a virtual world.
So to me, what is amazing is that we humans, with our brains, which are still limited, and and also maybe this started I don't know, last 100 years or so. Anyway, it's amazing to me that we as humans can even grasp so much, and that we were able to understand such a long, to look back now, speaking of the universe, but to look back and understand this history of the universe and come up how it could have happened, but also with ways of, you know, how to test these ideas, right? Of the Big Bang, of the evolution, and so on. So yeah.
We are a tiny part, but corresponding part, I suppose, in a universal brain.
Oh, you mean the universe? You mean something like the Boltzmann brain or so? Yes, who knows? Who knows?
Who knows? Yeah.
Yes. But yes, I also enjoyed
why
very much the lecture on because I read, and I just want to tell this to Maria, because I read a lot of poetry. It's just fascinating. I think there's a lot of connections between science and art, and I really need to read also poetry, which for me is the essence of writing.
Yeah.
You know, to just be able to to function. And one of my favorite books is also this Fragments of Sappho by Anne Carson, that I'm sure you probably know. It's a book that I read quite often. So yeah, so thank you very much for this nice lecture.
Yeah, so Violeta has a very good idea to bring science and art together. So congratulations to Violeta as well.
No, it is a definition of our academy.
maybe we can conclude.
We are so happy to be together and to discover such universes in our soul and all over us. So it's wonderful. I thank you so much, and we wish you a wonderful Christmas time, wonderful New Year, and see you again soon in the next year. We still have 2 more colloquium in this winter time. Thank you so much. Thank you,
Thank you also very much.
Take care.
Very nice to meet
Merry
everybody.
Christmas.
Happy New Year.
Happy
Bye.
New Year.
Bye.
Thank you, Jeremias. Thank you, Annette.
Bye-bye.
Bye. Bye.